I'm Gati, and I interned at the Software and Application Innovation Lab. We all know that information is power, and protecting the privacy of sensitive information is important. However, the need for privacy often locks information up and obstructs useful data analysis. For example, several hospitals might want to find out what patients they have in common, but they're not legally allowed to disclose their list of patients. A solution to this problem is secure multi-party computation, or MPC for short. MPC allows parties to mask their input values and perform a joint computation. At SAIL, they're working on an MPC framework called GIF that will make it easier to construct custom complex MPC protocols for web applications. My contributions to GIF include implementing a data-oblivious sort under MPC, creating a web application, Battleships, to demonstrate GIF's usability, and using Battleships to develop better algorithms for checking where sets of secret shares intersect. Shellsort was my first MPC implementation, but the Battleships GIF demo was my main focus. In the MPC version of Battleships, the locations of ships, guesses, and matches are private, but the amounts of each are public. Each answer corresponds to one guess, and both players should know when a guess matches a ship. In my first successfully implemented MPC Battleships program, I noticed a big issue. My code worked, but it took 5 minutes per turn. That's really slow. This motivated the next phase of my project, developing faster algorithms for checking equality within number sets under MPC. My original approach was slow because GIF's secret share equality function itself is slow, and I was calling it for each guess and for each ship, meaning 5 times 15 equals 75 times per function call. Now, there were 2 ways I could optimize this. One was finding a way to check equality without calling the GIF equality function, and another was making the GIF functions more efficient by reducing the size of the ZP value, which is a prime number that the secret shares are modded over and is larger than the largest secret share value. So my first optimization took advantage of the fact that the difference of 2 equal numbers is 0, and that 0 multiplied by any other number is 0. I also took advantage of the public range, 0 to 63, to reduce the ZP from a billion something down to 67. These optimizations allowed me to bring the average time all the way down to 2.7 seconds. However, I was not satisfied. I knew I could bring the ZP down even further, which would hopefully result in a faster algorithm. My next MPC version took advantage of how all the ships, guesses, and match locations could be represented as 1s and 0s on a 64-slot array. In this binary version, I multiplied corresponding ship and guess slots to get a 64-slot answer array. If both slots had 1, the product was 1. If either was 0, the answer was 0. This version on average took 2.8 seconds. Now, the binary version was fast, but it wasn't noticeably faster than the previous index comparing version, despite having a smaller ZP. I hypothesized that the binary version was spending the bulk of its time opening a huge 64-slot answer array, instead of a 5-slot answer array like in the index version. If this was the case, a compromise between the binary version's small ZP and the index version's small answer array size, say an algorithm that checked for equality in row-column pairs, would be very fast. However, my assumption was incorrect because the numbers are open in parallel, so opening a huge array does not actually slow down the function as much as I thought, and checking for equality within 2 pairs required more calculations than checking for equality within 2 numbers. My fastest row-column algorithm had a ZP of 149 and took 4.6 seconds, which is faster than the original 5 minutes, but slower than the other 2 versions. My final task was to analyze which version would be ideal for which situation. Ultimately, since the binary version uses only independent parallel multiplications, it is better in situations where the board is bigger, response delay is high, and bandwidth is large. The index version chains multiplications together, so response delay affects it more, but it has the advantage when there are small amounts of ships and guesses. The row-column version suffers from the same multiplication chaining as the index version, but it doubly suffers because it has a greater number of calculations and a big ZP. There is no situation where it will outperform either the binary or an index version. If you want to know more about the specifics of my research, you can read my paper, Refining Private Set Intersection under MPC. Thank you.